Now then, now we start. Here. So there's an exam next week. The request was to go through the entire review sheet. Are there any particular questions anybody has, or should we just start from the top? Yeah. Take it from the top. Okay. Draw a Cayley digraph for Z8 using 2 and 7 as your generating set. That's weird. Okay. If I have 2 and 7 as a generating set, I need a list of all, first I need all the elements in Z8. What are the elements of Z8? So I have the numbers 0 through 7. I need to know what gets generated by 2. I need to know what gets generated by 7. I need to know how the operation adding 2 works on all of those elements. And you know how the operation adding 7 works on all of those elements. So one of these needs to be an arrow for adding 2. And then I need a different kind of arrow for adding 7. So I'm going to go ahead and use this black arrow to mean +2. I'll just go ahead and switch colors and use this brown arrow to mean adding 7. And now we make a list of the numbers from 0 to 7, and we start anywhere we want. And from each one, we draw an arrow of each color. Yes, Ian.
Quick before we move on, I just wanted to ask real quick. Next to my graph that I have written, I put the line thing in order to indicate which one meant which. But I put squiggly bracket 2 equals the line. Is that okay notation?
Well, because we're technically not using a set,
right.
I didn't want to use that. I'm using it as an operations, that's why I put the plus on it. But I would understand what you meant by that. I wouldn't have a problem
You
with
wouldn't
it.
mark off points for that?
No. Okay, where are we starting? Okay. Want to do twos or sevens? Okay. So 0 plus 2 is 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 0. Because I'm adding in Z8. But notice, I missed a bunch of numbers. Every number should have an arrow for 2 coming out of it and going into it. I've missed all the odd numbers, so pick one and we'll start there and we'll make another set of arrows. If I start with 1, 1 goes to 3, 3 goes to 5, 5 goes to 7, 7 goes back to 1. So everything has an arrow going in and coming out in black. Now for the brown arrows. Same deal. Pick a number, start adding 7. Every number should have an arrow out from 7, being added to 7. Having 7 added to it, a number out. And an arrow in, it's the result of adding 7 to something. So where are we going to start? Okay, 0 goes to 7. What's 7 and 7?
14, but there would be 6.
Aha! 6 and 7 is 13. 5 and 7 is 11. 5 and 7 is 12. 7 and 4 is 11. Yeah. Hey, look at that. That's sufficient. It's not pretty, but it's certainly sufficient, right? How could I make this nicer? Well, I could try and align some of these numbers. I know that,
I was going to say, can you split up evens and odds?
sure. And I could say, I know that the evens are related by 2s. I know the odds are related by 2s. So I can make a pair of squares or diamonds or something and have the evens and the odds. You want the evens on the outside and the odds on the inside, or the other way around?
Evens on the outside.
Okay. Now, the reason I did them in that order is that I can go like this. Odds on the inside. All right. I can choose to put these odd numbers in any orientation I want. Let me think for a second. 0 and 7 are close together, aren't they? In terms of the other arrow. So instead of putting 1 here, I'm going to put 7 here. And then I'll make it look like that. Again, my arrows in black go like that, rotating clockwise around this group. But now look at the brown arrows. 0 to 7, 6, 5, 4 to 3, 2 to 1, 0. None of the brown arrows cross each other. Absolutely works. If you gave me, as long as I can follow what your arrows are doing. The important part is that I know that every arrow we've drawn up there matches an arrow we've drawn up here. They're the same picture. The bottom one's just pretty. Prettier. It's a relative judgment, right? No, this is absolutely correct. And I would see nothing wrong with that first picture, except I'd look at it and I'd go, ew. Now, more generators means more arrows. If we had 2 different colored arrows that were perfectly in sync with one another, then one of those generators would be redundant. They'd effectively be the same thing. If they were in the opposite direction, they would be generating the same sets. They would just be in reverse order. That's perfectly fine. Better? Okay. The second question gives me a permutation in S9. And it gives it to me in 2-row form. 3, 7, 4, 1, 9, 5, 8, 6, 2. So there's the 2-row version of the permutation sigma. So far, so good? First question, what are the orbits? How do I find orbits?
We're going to find the cycles.
Yes and no. Finding the cycles helps me find the orbits. Finding the orbits helps me find the cycles. But the orbits are sets, and the cycles are ordered. So there's a subtle, not required difference. So orbits give me cycles, cycles give me orbits, but just start applying a number. So 1 goes to 3, 3 goes to 4, 4 goes back to 1. That's technically a cycle, but the orbit would be the set 1, 3, 4.
So does the orbit have to be in that order? Or
No,
can we technically list
the
it?
orbit can be in any
That's the
order.
difference there.
Yes, the orbit is a set.
So the orbit just has to be in that set notation.
Right, that's the only difference. So I missed a number. Let's pick another number. 2 goes to 7, goes to 8, goes to 6, goes to 5, goes to 9, goes back to 2. And just because I could, I put the orbit in a different order than the cycle. The orbit is just a set. It's the numbers listed in any order you want. The cycle requires the order. And that's part B, because now I've got all of the numbers and I've got them in cycle order. So B as disjoint cycles, I keep the order in the same setup.
Do you want it as like sigma equals?
It's an option, but I'm trying to reflect this. I know you're working with sigma. If you all of a sudden put down numbers that aren't anything to do with our problem, I'm going to go, where the hell did you get this from? Okay. Turn those into transpositions. Each cycle becomes a set of pair flips. And there are 2 different ways to do this, depending on which version of the decomposition you want. So 1, 3, 4 can be written either 1, 4, 1, 3, or as 1, 3, 3, 4. I don't care which way you write it. I'm used to doing the first one, not the second one, but that's the way I was taught. Okay, so what happens? Remember, we're going to do sigma of 1 and I want to get 3, right? What happens to 1? And then what happens to 3 as I keep going from right to left? Nothing happens to 3. What happens to 3? 3 goes to 1, 1 goes to 4, so 3 ends up at 4. What happens to 4? Nothing. Oh, 4 goes to 1. So 1 goes to 3, 3 goes to 4, 4 goes to 1, just like I want here. What happens here to 1? Nothing. Oh, 1 goes to 3. What happens to 3? 3 goes to 4. Now what happens to 4? Nothing. What happens to 4? 4 goes to 3. Oh, but 3 goes to 1, so 4 ends up at 1. It gives me the same result when I compose it in either of those 2 ways. But I was taught to do 1 last, first, last, first, next to last. I was taught to do it in that order. So that's the one that's stuck in my head for years. I've got to do it for this one as well. 2, 7, 8, 6, 5, 9 is either 2, 9, 2, 5, 2, 6, 2, 8, 2, 7, or 2, 7, 7, 8, 8, 6, 6, 5, 5, 9. Your choice. And it says write sigma as a product, so take 1 from column A and 1 from column B, and you've got the whole thing. Yes, Ian.
Does one of those ways provide a mathematical advantage that the other doesn't?
I wish that were true. No.
Okay.
I hadn't seen that second version until I think only either 2 years ago, the last time I taught this course, or 4 years ago, the time before that. It's a fairly recent version to me, but someone saw it in another book and said, "Can we do it this way?" I'm like, "Yes, that works too." Okay. In one sense, that first one uses the first part, the first number in your cycle as an anchor and descends everything from it.
Yeah.
The other one does interchanged pairs, so it's kind of sequential. I'm sure if we did digraph behaviors or actions on sets, there's a graph theory version of digraph work that goes with this, like the Cayley digraph, that would show me some things differently between the two, but I've never explored that. There's a paper there for somebody. Okay. Each cycle is broken down to a product of transpositions. I need the order of sigma. How many times do I do sigma before I get back to where I started?
But we need to find the order of both of our separate sets there.
Okay.
And then we need to find the least common multiple. And that would be our order.
So I need the order of each cycle. Advantage. The order of a cycle is the length of the cycle. Least common multiple of 3 and 6. Yay. If you wanted, you absolutely could do this the longest possible way. By writing out sigma, sigma squared, sigma cubed, sigma to the fourth, until you got back to the identity. I don't want to do that, but we could. Advantage, though, is that when you multiply a cycle by itself, you just skip that many through, right? So if I do sigma squared, that's 1, 3, 4, 1, 3, 4, 2, 7, 8, 6, 5, 9, 2, 7, 8, 6, 5, 9. Cycles that are disjoint commute. So I don't have to worry about the fact that I'm moving things across each other. As long as there are no numbers in common, I'm allowed to do that. So this is 1, 4, 3. Go twice, go twice, twice. Here, we go by twos. Oh, 2, 8, 5. 7, 6, 9. It decomposes into 2 cycles of length 3 when I do it by twos. If I do sigma cubed, well, 1, 3, 4. I wrote that one backwards there. 1, 3, 4. 1, 3, 4 3 times is the identity. But 2, 7, 8, 6, 5, 9 skips by threes. So that becomes 2, 6, 7, 5, 8, 9. And so on.
So whenever you're doing sigma cubed, you don't want to look at what you got for sigma squared. You just want to go back to the original.
I think it's easier that way.
Okay.
You can absolutely do sigma squared times sigma, but then you're doing 143 times 134. And then you've got to multiply right to left, and that's fine. You can absolutely do that. You get exactly the same result. Same thing with 285769 times 278659. You absolutely can do that way. It will work. But because I'm taking powers, I think it's easier to work with the original decomposition of sigma and do powers there.
Can you show how to do it for the 285769 problem?
Sure.
I don't know how you get 6.
285769 times 278659, right?
Oh, okay.
So this is the sigma squared part.
Yeah.
And this is the sigma part, right? So where's 2 go? 2 goes to 7. I'm working right to left. 2 goes to 7. 7 goes to 6. 6 goes to 5. 5 goes to 2. 6 goes back to 2. So that's a closed cycle right there. And then I've done 2 and 6, so now I need another number, 7. Where does 7 go? 7 goes to 8. Oh, but 8 goes to 5, so 7 goes to 5. 5 goes to 9, but 9 goes back to 7. That closes that. And so on.
Okay, thank you.
I'm always working it right to left in this setup.
8, 9, so 2, 6, and then 7, 5, and 8.
Yes, because 8 goes to 6, 6 goes to 9, so 8 goes to 9. 9 goes to 2, 2 goes to 8, so 9 goes back to 8. Part E says sigma raised to the what giant power? I'm sorry. E says sigma to the 250th. Dear Lord, that's nasty. But every time I do 6 of them, I get back to the identity to know what the remainder is when I divide by 6. 150 is something times 6 plus something. Gee, it's discrete again. Quotient remainder. What's my quotient? What's my remainder? 41 and 4. Great. But that means that what I really need is sigma to the 4th. Because sigma to the 250th will be sigma to the 41 times 6 plus 4. That'll be sigma to the 6th to the 41st times sigma to the 4th. But that's the identity. Now I just have to work out sigma to the 4th. Which is 1 shy of where I was up there, right? But I can do it directly from the original. If I hadn't done any of these calculations, I could still do it. Sigma to the 4th is 134 to the 4th. 278,659 to the 4th. We're going to count through it 4 times, right? 1, 2, 3, 4. 1 goes to 3. 1, 2, 3, 4. 3 goes to 4. 1, 2, 3, 4. 4 goes back to 1. Wait a minute. Sigma to the 3rd was the identity up there, right at the top of the screen. Aha. And sigma to the 4th is sigma for that part. What about this part? Go by 4 is 1, 2, 3, 4. 2 goes to 6. Wait. 1, 2, 3, 4. 2 goes to 5. I can count. 5. 1, 2, 3, 4. 5 goes to 8. 1, 2, 3, 4. 8 goes to 2. We'll close that off. I skipped the numbers. Go to 7. Where does 7 go? 1, 2, 3, 4. 7 goes to 9. 9 goes to 1, 2, 3, 4, 6. 6 goes to 1, 2, 3, 4, 7. I'm closed off. It's a lot faster if I do it by counting by however many my exponent is.
Does it always work out that like you have a cycle of length like x would be raised to the x power step?
It should be. That's one of the easiest pieces to prove, that the orbit of a cycle is the length of the orbit. Isn't that kind of our definition? Sorry, the order of a cycle is the length of the orbit. More questions, ask me more things. No wonder I'm confused. I don't have the clock in front of me. I don't know what time it is. There. Okay. In Z30, I'm looking for cosets. So I need, it says find the cosets, not just count them, find them. So I need to know what the cosets are. And it says specifically left cosets. So the first thing I need is
You want to find the whole set generated by 6 or?
yes, that's where I have to start. So I need the subgroup generated by 6. So I start with 6. What do I do? 12, 18, 24, 30. But 30 is 0 in this universe. Okay, left cosets. Left cosets means I do what? So I'm going to add on the left side. What am I going to add? But 0 is in here. So 0 plus the group 6 is the subgroup generated by 6. So I don't need that one. This is automatically 0 plus 6. So I can start with 1. Before I go any further, how many cosets should I have? Including the original itself, I should have 6. Question? Oh, I'm sorry, I missed the other figure. So that means 1, 2, 3, 4, 5, 6. That should be the complete list. So I do the same thing. Please notice, every element between 0 and 29 appears in exactly one of these sets. We have a partition. These are equivalence classes. Equivalence relation formed by being in the same coset. 1 through 5, 0 through 6, 0 through 5, 6 through 11, 12 through 17, 18 to 23, 24 to 20. They're all there. Part B says find the right cosets.
So since H would generate all of Z30, that means that it's abelian, meaning that each element commutes, right?
You've said things that are true and you've said things that are false, so there's confusion here. H didn't generate the whole group. H itself is a subgroup. It's the things generated by 6. The cosets of H give me all of the group. But that doesn't make it abelian. Jalen? Ben?
Just because since it's in Z30 and Z, the integers,
The integers are abelian. That's where I can get this from. Which means right cosets and left cosets are the same. I'm done. I didn't have to do anything. Except say Z30 is abelian, so A plus 6 equals 6 plus A for all A. Which means this is a normal subgroup, if I want to use that terminology. Normal means the left cosets and the right cosets are equal. In any abelian group, every subgroup is normal. I'm done. No, it would be worth doing. I just don't have one at the top of my head. Do I have one on the review sheet? If not, we'll make one up. So yes, just give me a moment. Let me finish this problem and then we'll do it. C says find Z30 colon subgroup generated by 6. What the hell does that mean?
We're looking for the index, right?
Okay, what's the index? This is the index of the subgroup generated by 6 in Z30. What is an index?
that's the number of like cosets that we can use in the index.
Which in this case, I've already listed them. I know exactly how many left cosets I have. I got 6. But even if I didn't, I have finite groups. And in a finite group, the order of the subgroup, the index of the subgroup is the order of the group divided by the order of the subgroup. And we counted the number of things that were in the subgroup generated by 6. 0, 6, 12, 18, 24. There were only 5 of those. There we go. If I need to find the right cosets as compared to the left cosets, That means that my group G must be non-abelian in the first place. To me, that screams I've got to be working with a group of permutations. Maybe it's one of the dihedral groups, maybe it's one of the S groups. So let's consider S3. Here's the hard part. If I want to do this calculation, I need to remember how to multiply those. Put it politely. Either I need to know what those are in terms of permutations and multiply them as permutations, or I need to remember how to multiply mu's and rows together. And that was just so much fun, wasn't it? I wrote this one backwards. No wonder I'm looking at this wrong. See what I mean? The problem is memorizing all of these, and I've forgotten them. There's a table for S3 in the book, though, right? Might be a table for D3. This is my problem. In order for me to do this one, remember how to multiply these permutations. So let's do it that way instead. Okay, row times row is row squared. Row times row squared is the identity. Row squared times row is the identity. Row squared times row squared is row. Multiplying rotations is easy. It's when I start doing the mu. P times mu, row times column, is mu row squared. P times mu P is P mu is mu P squared. So that's mu P cubed, but P cubed was the identity. So that's just mu. And that means this has to be mu P. Because in each row, you can get each one only once. Row squared times mu is row times row mu. But we just said row mu was mu row squared. So that's got to be mu row squared. That's mu row to the fourth, but row to the fourth is P, so that's mu P. Isn't it fun?
This is on our exam rating.
I better give you the table. I just don't have it in front of me, so I'm generating it, right? Like I said, I can do this. It's just not simple. Yes, without the table, this would be a nightmare. But since this is not commutative, this is why I would need the table in front of me, because the left cosets and the right cosets won't be equal without the table. So if I'm going to give this to you, I better give you the table. Want me to keep going?
So if we were given a group and we didn't want to do this, like but say we didn't know whether we had to or not, we would first want to find whether the group is abelian. All right, that would definitely be the first step here. Okay.
So like, if we wanted to find the left cosets, would we look at like the top row and then look at the left, like the first subcolumn, look at what generates from that, and then the right cosets would be like, look at this and see what you get when you multiply this way.
Yes, because it's row, column in the table. So it's row is on the left, column is on the right. So the left cosets we read across the rows, right cosets we read down the columns. S3 is small enough that we already did this in the homework. There are only 4 subgroups here. The 4 subgroups of S3 are subgroup generated by row, subgroup generated by mu, subgroup generated by mu row, and the subgroup generated by mu row squared. Why do I know those are the only possible subgroups here? Oh, sorry, there's one other subgroup, and that's the boring one. Just the identity. Those are the only proper subgroups. Why do I know that? Has nothing to do with the fact that it's S3. It has to do with order. A group of order 6, right? Group of order 6, the only things that divide 6 are 1, 2, and 3. Your subgroups are either of order 1, order 2, or order 3. That's it. And the mirror elements are their own inverses. Mu row squared times mu row squared gives me I. Mu row times mu row gives me I. Mu times mu gives me the identity. Flip them back. So those are subgroups of order 2, and the rotations only generate more rotations. I can't flip 2 numbers if all I'm allowed to do is turn the knob. These would have different left cosets and right cosets. This one is normal. Without doing any crazy psycho calculations, why do I know that's normal? Takes me a minute to do the work. Why do I know this is a normal subgroup? This goes back to Thursday. Maybe Tuesday. If rho is a normal subgroup, then it's got a right coset and a left coset, yes? Rho itself consists of I, rho, and rho squared. The coset consists of 3 other elements, but there only are 3 other elements, aren't there? So if this is I, rho, rho squared, this must be mu, mu rho, and mu rho squared. And that's everything else, isn't it? Now do the right cosets. Rho, I, rho, rho squared. Rho mu is mu, rho mu, rho squared mu. But rho mu is mu rho squared. And rho squared mu is mu rho. They're the same. That's the long way to do it. The short way. There's the set I, rho, rho squared. That's set 1. There's everything else. That's set 2. There's only one coset available. Whether you multiply on the left or multiply on the right, you have to get this other set. This subgroup is A3. It's the even ones. That's why I wrote them out like this. This is 2 transpositions. This is 2 transpositions. This is 0 transpositions. These are all 1. This is A3. A3 is normal in S3. AN is always normal in SN. I'm a sneaky bastard. This has been an interesting diversion into non-abelian groups, but it's not part of the review, so it makes sense, I hope. I promise I'm not pulling shit out of nowhere. Better, worse, still iffy? Still iffy. Take a read through this one carefully. Next question is about order again, right? Non-isomorphic groups, right? So we're looking at groups of order 225. That phrase right there, up to isomorphism, tells me that I'm going to use the decomposition of cyclic groups. Zn is cyclic. What do I need to be able to do that? Of which is fairly easy. Great, now what?
So that tells us that a group of order 225 is a product of groups whose orders are powers of 3 and 5, meaning that we have Z9 and which can be broken down into Z3 times Z3, and Z25, which can be broken down into Z5 times Z5 as well.
So there are my four options. Leave them together, or break them apart one at a time, or break them both apart. The first one we wrote, this one, those orders, those indices are relatively prime, 3 squared and 5 squared. So this is the one that's actually isomorphic to Z225, which is why I didn't write that one down as an option. It's isomorphic to one of the ones we were given. And it says up to isomorphism, so I don't need to include it two ways, I only need to include it one. So there are only four. Questions? So this question asks, is this map a homomorphism? How do I know if something's a homomorphism?
If it obeys sigma of x of y equals sigma of x, sigma of y.
This isn't sigma, this time this is phi.
Or, sorry,
Okay. So I need phi of x and phi of y. Phi of y is the absolute value of y. What is phi of xy? Well, that's the absolute value of xy. How's that related to these? That's my homomorphism property. Check. And I know this statement is true from algebra class. Like way long ago, basic algebra class. All right. This is a homomorphism. What's the kernel of this homomorphism?
Anything that maps to 1, since we're multiplication, so it'd be like x equals -1 and 1.
Exactly. It's the set of elements that map to our identity. In that case, here's a stretch. The kernel, the homomorphism. Think of our fundamental triangle. There are cosets to that, aren't there? And since we're in the real numbers, each coset is the same size as that. And we're multiplying. So pick a real number other than 0, because it says R star up there. Multiply by this, you get plus that number minus that number. Every coset has 2 elements visually. The real numbers other than 0 form a line with a hole in the middle. This map folds that line in half. And every number, the negative lands directly on the positive, doesn't it? It's a 2-to-1 map because the kernel is of size 2. Questions? Apparently, I'm not going to make it through the whole thing. So I've got what, three or four more to go? 5 more to go? How many more are there? 4? All right. So 6, 7, 8, and 9. Which one do you want? And if we get through it, we'll move to the next one. 8. Prove or disprove there is a homomorphism phi from Z10 to Z3, which maps onto. Okay. Is there a homomorphism that maps onto? That's Z3, right? If I do the homomorphism property onto, means I have to get each of those 3 elements. Yes? That means a number of things are going to go to 0. How many things are going to go to 0? I don't know. But whatever it is, it has to divide up my domain into equal pieces. But there are 10 things in the domain, aren't there? Does 10 divide evenly by 3? There we go. Yes, sir.
I ended up looking this one up after I did it because I was feeling weird about it.
That's okay.
And it said that mainly where we do is because Z10 lacks elements of order 3. Would you be able to explain that?
Okay. Because I'm going to map with a homomorphism, the identity has to go to the identity. So 0 goes to 0.
Right.
1 goes somewhere. Let's make the assumption that 1 goes to 1. Then 2 goes to 2, and I start repeating, right? But anything in Z10 either makes the whole group or a subgroup. What things divide 10?
2, 5, 1.
And none of those are 3, are they?
No.
So I can't keep repeating those 3s and not have something left over.
Right, so it is related to the order.
Exactly. And that's really what we've done here is I said, hey, this order does not divide evenly into the other one. There's no element I can use to get 3s over and over. I'm glad. Yes, sir.
So for number 9, a simple group just means that the only subgroups are the identity of the.
Correct.
So you just, so if I said like generated by 2 as a subgroup.
Show that it's normal. It's got to be a normal subgroup. It can have subgroups, but it can't have any normal proper subgroups other than 1 in the whole group. So it's that normal part that needs to be in there. I will post the key. All right? I will see you all on Thursday, where we're going to move onward, and you're going to turn in the last homework, and then I will post the key for that as well.